Before we dive in, please remember that the information in this video is for educational and informational purposes only. The career path and strategies discussed are based on industry trends and experience, but this presentation does not constitute professional career advice and does not guarantee employment or a specific income level. Your personal success will ultimately depend on your own effort, skills, qualifications, and the conditions of the job market. Always conduct your own thorough research. Picture this: you're scrolling through job sites. You see the same titles over and over: software engineer, mechanical engineer, project manager. The competition for every single role is absolutely brutal. You feel like you're just one of 1,000 resumes being fed into an algorithm, hoping to get noticed. You're looking for a real career, something with stability, something that's future-proof, but every path seems either oversaturated or on the verge of being replaced. But what if I told you there's a hidden parallel universe of engineering that is desperately, and I mean desperately, looking for people? A field where the demand is so high that companies are in a constant battle to find talent. A world that combines the digital and the physical, the code and the steel, to create the backbone of modern civilization. That world is engineering automation. And the crazy part? You don't need a PhD from MIT to get a seat at the table. What we're talking about today is the single most important shift in the American industrial landscape in the last 50 years. And you are in the perfect position to take advantage of it. This isn't just another video telling you to learn to code. This is a 5-step, actionable blueprint designed to take you from zero to a high-demand, high-impact career in automation, right here in the United States. We are going to demystify this entire industry. By the end of this presentation, you will have a crystal-clear roadmap. We'll cover the 5 essential steps. First, truly understanding the core pillars of automation, what this field actually is. Second, we'll build your foundational skill stack, the non-negotiable skills you absolutely must learn. Third, I'll show you the project over paper portfolio strategy, which is how you prove your value without 10 years of formal experience. Fourth, we'll dive deep into how to navigate the US job market specifically for these roles, where to look and who to talk to. And finally, step 5, we'll cover how to dominate your first 90 days on the job to set yourself up for a meteoric rise. So let's get into it. Step 1 is the foundation for everything else. Understanding the core pillars of automation. Because if you don't understand the battlefield, you can't win the war. Most people hear automation, and they picture a scene from a sci-fi movie. Robots that look like people building everything. That's not it. The reality is both more complex and far more interesting. Think of an automated system not as a single robot, but as a living organism with 4 distinct parts: a brain, its senses, its muscles, and a nervous system. If you can understand these 4 pillars, you understand the entire industry. Let's start with the most important one, the brain. In the world of industrial automation, the brain is almost always a PLC, which stands for Programmable Logic Controller. Forget everything you think you know about computers. A PLC is a special type of ruggedized computer built for one purpose and one purpose only: to run a machine or a process with extreme reliability, 24 hours a day, 365 days a year, without ever crashing. Your iPhone is amazing, but would you trust it to control a $10 million robotic welding line? No way. You trust a PLC. Learning to program these PLCs is the single most valuable skill in this entire field. It is the bedrock. And here in the United States, the market is dominated by one giant, Rockwell Automation, and their brand of PLCs called Allen Bradley. If you want a job in automation in the US, learning the Allen Bradley ecosystem is like learning English to do business. It is the default language. The second biggest player is Siemens, which is more dominant in Europe, but still has a massive presence here. Focusing on just these 2 platforms will make you instantly marketable to thousands of American companies. Think of a PLC programmer as the director of a play. You write the script that tells every actor, every motor, every valve, every robot exactly what to do, when to do it, and in what sequence. It's the core logic, the intelligence behind the entire operation. But a brain is useless without senses. This brings us to the second pillar, the vision and sensing layer. How does the automated system know what's happening in the real world? It uses sensors, thousands of them. A sensor that detects if a box is present on a conveyor belt. A sensor that measures the temperature of a liquid in a tank. A pressure sensor that ensures a hydraulic press doesn't crush apart. It's the eyes and ears of the factory. This pillar also includes something much more advanced: machine vision. This is where you use smart cameras and sophisticated software to inspect products at lightning speed. Is the label on that bottle straight? Are all the screws present in that engine block? Is there a crack in that phone screen? A human might be able to inspect a few of these a minute. A vision system can inspect hundreds flawlessly. People who understand how to select, install, and program these sensing systems are wizards in the industrial world. They give the machine the ability to perceive reality, which is the first step to controlling it. Once the brain has processed information from its senses, it needs to actually do something. That's the third pillar, the action layer, or what I call the muscle. This is where things get physical. We're talking about motors that spin conveyors, pneumatic cylinders that push boxes, hydraulic actuators that lift thousands of pounds, and of course the big one, industrial robots. The robots you see in factories, typically big robotic arms made by companies like Fanuc, ABB, or KUKA, are the heavy lifters. They weld car bodies, they stack pallets, they paint airplane wings. But a robot is just a very strong, very fast, very dumb arm. It's the automation engineer who programs its movements, integrates it with the PLC, and gives it a purpose. This pillar is where mechanical and electrical engineering crash into computer science. You have to understand how things move, how electricity makes them move, and how code can orchestrate that movement with precision down to the submillimeter level. So you have a brain, the PLC. You have senses, the sensors and cameras. You have muscle, the robots and motors. How do they all talk to each other? That's the fourth and final pillar, the network layer, the nervous system of it all. Decades ago, every sensor and motor had to be physically wired back to the controller, resulting in massive cabinets with miles of copper wire. It was a nightmare. Today, it's all done over industrial networks, which are basically super robust versions of the Ethernet you have at home. Technologies like Ethernet/IP and Profinet are the highways that carry all the information. The PLC sends a command to the robot over the network. The vision camera sends the inspection results back to the PLC over the network. It's the invisible, unsung hero of the entire system. You don't need to be a Cisco-certified networking guru, but you absolutely need to understand how these industrial protocols work. Understanding this layer is what separates the hobbyists from the professionals. It's how you go from controlling one small machine to orchestrating an entire factory floor. So let's recap the four pillars: the control layer, which is the PLC brain; the sensing layer, the eyes and ears; the action layer, the robotic and mechanical muscle; and the network layer, the nervous system that ties it all together. Your goal is not to become the world's leading expert in all four. That's impossible. Your goal is to become a T-shaped engineer. You have a broad understanding of all four pillars, but you go deep and specialize in one or two, most likely the PLC control layer to start. This makes you an incredible problem solver. When a production line goes down at 3 a.m. and the company is losing $100,000 an hour, they're not looking for a pure software developer or a pure mechanical engineer. They are looking for you, the person who understands how the whole system, from the sensor to the software, works together. You are the translator, the integrator, the one person who can see the entire picture. And in the American economy of today, an economy desperately trying to bring manufacturing back, to strengthen supply chains, and to become more efficient, that person is an indispensable asset. That person is you. Now that you have a map of the territory, you know what this field is actually about. The next, most critical question is, how do you get the skills? Where do you even begin to learn PLC programming, or robotics, or machine vision, without going back to college for another 4 years? That is exactly what we are going to cover in our next step, building your foundational skill stack. We will lay out the specific languages, the software, and the hands-on strategies you need to focus on to make yourself immediately valuable to any company looking for automation talent. Alright, so let's dive right into it. The term skill stack gets thrown around a lot, but in automation it's not just a buzzword, it's your entire toolkit. It's the difference between being the person who just follows instructions and the person who designs the entire system. But when you first look at job descriptions, it feels like you need to be a master of everything. A software developer, a mechanical engineer, an electrician, and a data scientist all rolled into one. It's overwhelming. And that feeling of being overwhelmed is the #1 reason people give up before they even start. They see a list of 20 different technologies and think, I can't possibly learn all of that. Here's the secret they don't tell you. You don't have to. You don't need to be an expert in everything. You need to be what's called a T-shaped engineer. Imagine the letter T. The vertical part is your deep specialized knowledge in 1 or 2 core areas. The horizontal part is your broad functional knowledge across the entire automation landscape. This T-shaped model is your roadmap. It allows you to be the go-to expert on something specific, while still being able to speak the language and collaborate with everyone else on the team, from the mechanics on the floor to the IT guys in the server room. So what does this T-shaped stack actually look like? Let's build it from the ground up, starting with the absolute, non-negotiable foundation. The first layer, the bedrock of your entire career, is PLC programming. Programmable logic controllers. If you learn nothing else from this video, burn this into your brain. PLCs are the industrial-hardened computers that form the central nervous system of virtually every factory, power plant, and automated warehouse on the planet. They are the workhorses. They read inputs from sensors like a button being pressed or a part arriving on a conveyor, and they make decisions to turn on outputs, like starting a motor, opening a valve, or moving a robotic arm. Thinking you can be an automation engineer without understanding PLCs is like trying to be a doctor without understanding human anatomy. It's the fundamental language of how things get done in the physical world. The dominant players in the United States are Rockwell Automation, with their Allen Bradley brand, and Siemens. If you're starting from zero, focus on Rockwell Studio 5000 and RS Logix 500. Why? Because they have an enormous installed base in North America. Walking into an interview and being able to say, "I understand ladder logic and I'm comfortable in the Studio 5000 environment," is an immediate green flag for hiring managers. Now, the primary language you'll use here is ladder logic. It looks a bit strange at first, like an electrical schematic turned on its side. But it was designed that way intentionally so electricians and technicians who were used to reading relay logic diagrams could easily transition. And that's its power. It's visual and intuitive. A line of code isn't just text. It represents a flow of electricity. When a set of conditions is true, the rung is complete, and power flows to the output. It's a beautifully simple and incredibly robust way to control complex machinery. Your goal here isn't to become the world's greatest ladder logic programmer overnight. Your goal is to understand the fundamentals: inputs, outputs, timers, counters, and basic data manipulation. That's the deep vertical part of your T for many starting roles. Okay, so you've got the central nervous system down. What's next? The second layer is the higher-level brain, scripting and programming, specifically with a language like Python. If PLCs are the fast, reliable workhorses that never get tired, Python is the intelligent, flexible supervisor that analyzes the data and optimizes the whole operation. This is where a lot of people get confused. They ask, why do I need Python if the PLC is already running the machine? Great question. The PLC is fantastic at real-time, deterministic control. You press a button, a light turns on instantly, but it's not great at handling large amounts of data, communicating with web services, or creating complex reports. That's where Python shines. Imagine a bottling line running with a PLC. The PLC makes sure every bottle is filled, capped, and labeled perfectly thousands of times an hour. But what if the plant manager wants to know the efficiency of that line over the last month? What if they want to predict when a machine might fail based on its vibration data? You are not going to do that inside the PLC. Instead, you'll use a Python script to pull the production data from the PLC or a database, analyze it using libraries like pandas and NumPy, and create a dashboard or a report that gives the manager actionable insights. You become the bridge between the factory floor and the front office. You're not just making the machine run, you're making the business run smarter. Your first project? Don't try to build a massive AI. Write a simple Python script that reads a CSV file, a spreadsheet of fake sensor data, and flags any values that are out of spec. It's a simple task, but it teaches you the core loop of automation intelligence. Acquire data, process it, and make a decision. This is an incredibly valuable and sought-after skill. Now we have the nervous system and the brain. The third layer is the eyes and hands, robotics and machine vision. This is the part that looks amazing on camera. The giant robot arms swinging car bodies around, the smaller cobots working alongside humans. The big names you'll hear are Fanuc, KUKA, ABB, and Universal Robots. And for vision, it's Cognex and Keyence. Here's the T-shaped principle in action again. You do not need a PhD in robotic kinematics to get a job. Most of the time, you won't be designing a robot from scratch. You'll be integrating a pre-built robot into a work cell. Your job is to teach it. You'll use a device called a teach pendant, which is basically a big, ruggedized tablet with a joystick, to move the robot arm to different points and record their positions. You'll program a sequence. Go to point A, pick up the part, go to point B, put it down. You'll integrate a vision system, a smart camera, to tell the robot exactly where the part is, even if it's slightly misplaced. Your goal is to understand the concepts of robot coordinate systems, world frame, tool frame, and basic I/O communication. How does the robot tell the PLC, "Hey, I've successfully picked up the part"? How does the PLC tell the robot, "Okay, you're clear to move into the machine"? Understanding this handshake between the robot and the PLC is 80% of the job. You can learn the basics of this on free simulators that many of these companies provide. You don't need a six-figure robot in your garage to start learning. Finally, the fourth layer, and this is one that software-focused people often forget, is the ability to read the blueprints, SCADA, and electrical schematics. Automation systems don't exist in a vacuum. They are physical installations of panels, wires, conduits, sensors, and motors. And the universal language to describe how these things are built is a drawing. You need to be able to open an electrical schematic drawn in something like AutoCAD Electrical and understand it. You need to be able to trace a wire from a PLC output card through a terminal block to a relay and finally to a motor starter. If you can't do this, you will be completely lost when it comes time to troubleshoot a real-world system. When a sensor isn't working, is it a bad sensor? A broken wire? A faulty PLC card? A coding error? The schematic holds the answer. Similarly, you need a basic understanding of mechanical drawings, often made in software like SolidWorks or Inventor. You don't need to be a mechanical designer, but you need to be able to open a 3D model of the machine, find where a specific sensor is supposed to be mounted, and understand the physical constraints you're working with. Trying to do automation without being able to read these drawings is like trying to assemble IKEA furniture with no instructions. You might get there eventually, but it's going to be painful, and something will probably be backward. So that's the stack: PLC programming as the foundation, Python for high-level logic and data, robotics and vision for interaction with the physical world, and CAD/schematics as the universal language. Now, the billion-dollar question: how do you actually learn this stuff? The key is project-based learning. Don't just watch endless tutorials. You need to get your hands dirty, even if it's virtual. Your mission is to build a portfolio of small, tangible projects. Buy an Arduino or a Raspberry Pi for $30. It's not an industrial PLC, but it has inputs and outputs. Wire up a button and an LED. Write a simple program that makes the LED blink 5 times when you press the button. Congratulations, you've just created a basic control loop. Now have it log every button pressed to a text file with a timestamp. You're now doing data acquisition. Send that data to a simple Python script that analyzes it. You're now doing IoT, the Industrial Internet of Things. Document every single one of these little projects. Take pictures, write a short blog post, or record a quick video explaining what you did and what you learned. This portfolio is now your proof. It's what you'll talk about in interviews. It shows initiative, passion, and the ability to solve problems. It is infinitely more powerful than a certificate from an online course. This hands-on project-based approach is the single most effective way to build your T-shaped skills and make yourself undeniable to employers. Building these skills is the most crucial step, but it leads directly to the next big challenge. How do you get experience when every job posting asks for 3 to 5 years of experience? It's the classic chicken and egg problem, but there's a way to solve it, a way to create your own experience from scratch, right from your own home. And that's what we're going to break down in the next step, the home lab revolution, and how you can build a portfolio that rivals someone with years in the field. So let's talk about that revolution, because what I'm about to share with you is the single most powerful strategy to bypass the entire entry-level job requires 3 years of experience paradox. This isn't just a tip, it's a complete shift in how you approach your career. The home lab is your personal research and development department, your factory floor, your proof of concept center, all packed into a corner of your desk or garage. Think about it from a hiring manager's perspective. They've got a stack of 100 resumes on their desk. They all look the same. Same degree, same GPA, same keywords copied from the job description. It's a sea of sameness. Then they get to yours. And on your resume, right at the top, is a single link with the words, "View my automation project portfolio." They click it. It doesn't go to a boring text document. It goes to a clean, simple web page or maybe a YouTube playlist. The first video starts playing. It's you speaking clearly to the camera for 15 seconds, and then the camera pans over to a small conveyor belt. A sensor detects a small block, the conveyor stops, a robotic arm swings over, picks it up, and places it in a box. The whole process is displayed in real time on a slick graphical interface on a nearby monitor. You've just demonstrated knowledge of PLCs, I/O sensors, robotics, and HMI development in 60 seconds. Who do you think gets the interview? The person who says they're a detail-oriented, passionate, quick learner? Or the person who just proved it, undeniably? This is the power of the home lab. It transforms you from a passive job seeker into an active creator of value. You're no longer asking for a chance. You're showcasing your capabilities. So how do you build one? It's a lot easier and cheaper than you think. We're going to break it down into 3 tiers, from a $0 starting point to the full-blown mini factory. Tier 1, the virtual lab. This costs you exactly $0. I repeat, you can start this tonight for free. The biggest players in the automation industry provide powerful software that you can use for free, either through trial periods or student versions. Your goal here is to learn the software environment where 90% of the work is done. First, download a PLC programming environment. For the Allen Bradley world, which is huge in the US, you want to look for Rockwell Studio 5000 Logix Designer. They often have 30 or 90-day trial versions. You can pair this with their simulation software, Logix Emulate. This lets you write real ladder logic, the same code that runs billion-dollar factories, and test it on a virtual processor right on your laptop. You can create timers, counters, complex logic sequences, and see how it all works without a single piece of hardware. For the Siemens ecosystem, which is dominant globally and very strong in certain US industries, you'll want to download their TIA portal. Siemens is fantastic about providing 21-day trial licenses that you can rearm multiple times. TIA portal includes PulkSim, an incredibly powerful simulator that lets you build and test your code on a virtual PLC. Your project in Tier 1 is simple. Learn the interface and master the fundamentals. Create a program for a virtual traffic light. Program a virtual garage door opener that won't close if a safety beam is broken. These are classic training exercises for a reason. They teach you the core logic you'll use every single day. Document your code. Add comments explaining what each rung of logic does. Save these files. They are the very first pieces of your portfolio. Tier 2, the physical trainer. Okay, you've spent a few weeks in the virtual world and you're comfortable. Now it's time to make your first small investment. You need to get your hands on a real PLC. This is the piece of hardware that makes a hiring manager's eyes light up. It shows you're serious. You don't need a $10,000 industrial controller. You need a trainer or a micro PLC. For the Allen Bradley side, look for a Micro 820 or a Micro 850. They are incredibly capable, affordable, and you can program them with the free Connected Components Workbench software. For Siemens, look for a Logo or an S7-1200 series PLC. These are the workhorses of small-scale automation. Where do you get them? eBay is your best friend. Search for PLC Trainer. You'll find dozens of kits, often sold by hobbyists or other engineers, that include a PLC, a power supply, and a set of buttons and lights, all mounted on a neat little board. You can often get a complete, ready-to-go trainer for a few $100s. That's less than the cost of a single college textbook, and I guarantee you it's 1,000 times more valuable for getting a job. Your project in Tier 2 is to take the virtual programs you already wrote and make them work in the real world. Wire a physical button to an input on your PLC. Write the logic so that when you press that button, a physical light connected to an output turns on. It sounds simple, but the first time you press that button and that light clicks on, the first time your code affects the physical world, it's a magical moment. You've just bridged the gap between digital and physical. Document this. Take a video with your phone. Show the wiring. Show the code on your screen, then press the button and show the light. You're now demonstrating hands-on hardware and troubleshooting skills. Tier 3, the full-stack mini factory. This is the final boss. This is the setup that makes you look like you have 5 years of experience. This is what you put in that portfolio video that gets you the job. It involves integrating multiple components into a single, cohesive system. Your shopping list here expands, but you can do it smartly and on a budget. You still have your PLC trainer at the core. Now you add a few more pieces. First, a small conveyor belt. You can find many hobbyist conveyor belts on Amazon or AliExpress for under $100. Second, sensors. You need a simple photoelectric sensor to detect when an object is at a specific point on the belt. Again, Amazon, a few dollars. Third, an HMI or human-machine interface. This is the screen that operators use to control the machine. You don't need to buy a physical one. You can run HMI software right on your PC that communicates with your physical PLC. Check out Inductive Automation's Ignition. They have a free version called Ignition Maker Edition that is unbelievably powerful and completely free for personal use. Finally, the secret weapon, a small cheap robotic arm. Again, think Amazon or U-Factory. You can get a simple 4-axis arm for a couple $100s. It won't be building cars, but it can pick up a bottle cap. Now, you combine it all into a single project. The miniature bottling line. An object, a bottle cap, a Lego block goes on the conveyor. It moves. The sensor sees the object and sends a signal to your PLC. Your PLC logic stops the conveyor motor. It then sends a signal to the robot arm to execute its pick-and-place or fill routine. Once the robot is done, it signals back to the PLC. The PLC then restarts the conveyor. The entire time, your Ignition HMI on your laptop is showing a graphical representation of the system. The conveyor is running, the sensor is tripped, the robot is active. You can even add start/stop buttons on the screen. This single project demonstrates more skills than most graduates learn in 4 years of theory. You're showing PLC programming, hardware I/O wiring, sensor integration, motor control, HMI design, and systems integration. The final and most critical part of the home lab revolution is documenting your work. A project that nobody sees is just a hobby. A well-documented project is a career maker. Here's your documentation strategy. First, record everything with your phone. Short 30 to 60-second clips. Explain the goal, show the system running, and briefly explain the result. No need for fancy editing. Just clear, concise proof. Second, create a GitHub account. It's free. This is where professional software developers store their code. You're going to do the same. Upload your commented PLC ladder logic. Upload your HMI project file. If you drew a little wiring diagram, even on a piece of paper, take a picture and upload that too. This shows an unbelievable level of professionalism. Third, build your portfolio. This can be a free website on Google Sites, a LinkedIn article, or just a simple YouTube playlist. For each project, embed the video, write a short paragraph explaining the challenge and your solution, and this is key, provide the link to your GitHub repository. When you walk into an interview, you're not just bringing a resume anymore. You're bringing a portfolio of tangible working projects. When they ask you, tell me about a time you solved a difficult problem, you don't give them a vague story about a college class. You pull out your phone, play the video of your mini factory and say, let me show you. You've just changed the game. You've taken control. You've built your own experience. Now you have this incredible, undeniable proof of your skills. But proof is useless if the right people don't see it. So, how do you get this portfolio in front of the hiring managers and senior engineers who matter? How do you turn a YouTube link into a job offer? That's all about strategically building your network and crafting a resume that can't be ignored, even when you're starting from scratch. And that's exactly what we're diving into next. Let's start with the hard truth. Your resume is not a historical document. It's a marketing brochure. And right now, the product it's selling is you. The problem is most people write their resumes like they're writing their own obituary. A boring chronological list of things they've done. Attended this college. Worked at this place. Familiar with this software. It's a passive document that screams, please just give me a chance. And in the world of automation engineering, that resume gets deleted in less than 6 seconds. Often by a robot. We need to change the game entirely. We're not creating a historical document. We're forging a key. A key specifically designed to unlock one thing, the automated gatekeeper, the applicant tracking system or ATS, and then the mind of a human hiring manager. So step 2, forge your key. This is about building a resume that doesn't just list your experience. It proves your value. Forget the old format. We're building a project-based resume. Here's how it works. Instead of a work experience section, you're going to have a relevant automation projects section. This is your prime real estate. This is where you put that home automation project, that PLC traffic light you built, that Python script you wrote. Because here's the secret. For an entry-level role, a hiring manager cares less about your part-time job scooping ice cream and more about the fact you voluntarily spent 40 hours wrestling with ladder logic because you were genuinely curious. One shows you can show up on time. The other shows you have the passion and the grit to be an engineer. For each project, you're going to use the CSR formula. Challenge, solution, result. First, the challenge. What was the problem you were trying to solve? Don't just say, I wanted to build a robot arm. Frame it like an engineer. Challenge, to design a low-cost, 3-axis robotic arm capable of sorting objects by color with 99% accuracy. See the difference? You've already embedded keywords like design, 3-axis robotic arm, and accuracy. Next, the solution. This is the how. This is where you detail the tech stack in your process. Solution: developed a control system using an Arduino Mega, programmed in C++, integrated a color sensor and utilized servo motors for precise movement, designed and 3D printed custom enclosures and grippers using SolidWorks to minimize weight and cost. Look at what you just did. You've naturally woven in Arduino, C++, sensors, servo motors, SolidWorks, and 3D printing. You're not just listing skills, you're showing how you applied them in a real-world context. Finally, and this is the most important part, the result. You must quantify everything. Numbers are the language of engineering and business. They are undeniable proof of impact. Result: achieved 98.5% sorting accuracy, a 20% reduction in projected cost compared to off-the-shelf components, and documented the entire project on GitHub, complete with schematics and source code. That last part, linking to your GitHub or a YouTube video of the project in action, is the knockout punch. You're not just telling them you can do it, you're showing them. Now you might be thinking, but I don't have any projects. We covered that in the last part. Your mission starting today is to build one, even a small one. The world is full of problems. Automate something in your own life. A plant watering system, a pet feeder, a script to organize your files. The scope doesn't matter as much as the process. Document it. Use the CSR formula. That one project is now more valuable on your resume than a 4.0 GPA with zero application. This project-based approach does two magical things. First, it bypasses the ATS robots because it's naturally packed with the keywords and technical terms from the job descriptions. Second, when a human finally sees it, it tells a story. It shows initiative, problem-solving skills, and a genuine passion for the field. You're no longer just a candidate. You're an emerging engineer. That's your key. But a key is useless if you can't find the right lock. That brings us to step 3, find the lock and get the introduction. This is networking, but not the slimy transactional, will you be my connection? Kind of networking. This is strategic intelligence gathering. Your goal is not to ask for a job. Let me repeat that. Your goal is not to ask for a job. Asking a stranger for a job is like walking up to someone and asking them to marry you. It's desperate, it's awkward, and the answer is always no. Your goal is to ask for advice. People love giving advice. It makes them feel smart and respected. Here's the mission. You are going to use LinkedIn not as a job board, but as a company directory. Find 10 companies in your target area where you'd love to work. Now, find people who have the job you want in 5 years. A controls engineer, an automation specialist, a senior systems integrator. These are your targets. You are going to send them a connection request, but you must add a note. A note that is short, respectful, and focused on them, not you. Here's a template. Hi name. My name is your name, and I'm an aspiring automation engineer. I came across your profile and was really impressed by your work on, mention a specific project or their experience at their company. I'm not looking for a job, but I am trying to learn from professionals in the field. Would you be open to a 15-minute virtual coffee chat in the coming weeks to share some advice on how you navigated your career path? Let's break down why this works. 1. It's specific. You mention their work, which shows you did your homework. 2. You explicitly say, I'm not looking for a job, which immediately lowers their defenses. 3. You make a specific low-friction ask. 15 minutes. Everyone has 15 minutes. This is a request that is easy to say yes to. Let's say you send out 10 of these. 7 will ignore you. That's fine. 2 will accept the connection but won't reply. That's also fine. But 1 will say yes. That one yes is a gold mine. Now you have the meeting. What do? You prepare. You have a list of smart questions ready. Not so what do? You can find that on their profile. Ask better questions. What's the most challenging project you've worked on and why? What's a skill you thought was critical when you started that turned out to be less important? And what skill do you wish you had focused on more? What does a successful first year look like for a new engineer on your team? You are gathering intelligence. You are learning the language, the culture, and the real-world problems of the company from an insider. At the end of the 15 minutes, you thank them for their time and ask the magic question. Based on our conversation, is there anyone else you think it would be valuable for me to talk to? They might connect you with a colleague, a manager, or someone in a different department. You are expanding your network one trusted introduction at a time. After the call, you send a thank you email. And a week later, you send a follow-up. Hi name. Thanks again for your advice last week. You mentioned I should look into structured text programming, so I spent the weekend learning the basics and completed a small traffic light simulation. It was a fantastic learning experience. Just wanted to say thanks for the guidance. You see what's happening? You're building a relationship. You're demonstrating that you're coachable, you take initiative, and you follow through. You are now no longer a random student. You are a promising up-and-comer on their radar. Do this 5 times and you'll have 5 insiders at 5 different companies. When a junior position finally opens up at one of those companies, you don't apply through the front door like everyone else. You send a polite message to your contact. Hi name, hope you're well. I saw the new junior controls engineer position opened up. Based on our past conversations, it feels like a perfect fit for my skills, especially with the project work I've done in ladder logic. Would you be willing to pass my resume along to the hiring manager or offer any advice on applying? You've just turned a cold application into a warm referral. Your project-based resume, your key, doesn't go into the giant pile of 300 other resumes. It gets hand-delivered to the decision-maker by a trusted employee. You have successfully bypassed the gatekeeper. This is the system. Forge the key with a project-based resume that proves your worth. Find the lock by building genuine relationships and gathering intelligence. This is how you go from zero experience to a top-tier candidate. You now have a resume that can't be ignored and a network ready to advocate for you. The door is about to swing open, and on the other side is the technical interview. This is the final boss battle. It's where they separate the people who can talk about engineering from the people who can actually do it. And many brilliant candidates with perfect resumes freeze up and fail, not because they don't know the answers, but because they don't know how to think like an engineer under pressure. They get hit with a specific type of problem-solving question designed to test their very thought process, and they crumble. But you won't, because we're going to break down that exact process next. So let's put you in the hot seat. You're in the final interview for your dream automation job. The hiring manager leans forward and says, "All right, let's try a hypothetical. I want you to walk me through how you would design a machine to automatically sort a big bowl of M&Ms by color." And this is the moment. This is where 90% of aspiring engineers crash and burn. Their heart rate spikes. Their mind goes blank, then floods with a dozen different disconnected ideas. They start talking about specific sensors, maybe a Raspberry Pi, they mention conveyor belts and servo motors. They're grabbing at technical details, trying to prove they know stuff. But what they're actually proving is that they don't have a process. They're just throwing spaghetti at the wall and hoping something sticks. You're not going to do that. You're going to take a deep breath, maybe even smile a little, because you have a secret weapon. It's a 4-step mental framework that you can apply to any open-ended engineering problem, from sorting candy to designing a fully automated warehouse. This framework will instantly signal to the interviewer that you are not a junior candidate who needs hand-holding. You are a professional problem solver. The framework is simple: clarify, deconstruct, solutionize, and validate. Let's walk through it with our M&M problem. Step 1, clarify. This is the most important step, and it's the one almost everyone skips. Before you propose a single piece of hardware, you become an investigator. You ask questions. You don't make assumptions. You define the problem so clearly that there's no room for misunderstanding. You might say something like, "That's a great question. To make sure I design the right system, I have a few clarifying questions. First, what's the scale of this operation? Are we sorting a single bag of M&Ms for fun? Or are we talking about an industrial process sorting thousands of pounds an hour?" The interviewer's answer changes everything. A machine for your desk is wildly different from a factory-scale machine. Then you keep going. What are the performance requirements? How fast does it need to sort, let's say, in M&Ms per minute? And what's the required accuracy? Is 99% accuracy acceptable? Or does it need to be perfect? What happens to M&Ms that are chipped or have a faded color? See what's happening here? You're not just answering their question. You're showing them how you think. You're thinking about throughput, quality control, and edge cases. And finally, the ultimate engineering question. What are the constraints? Is there a target budget for this machine? Are there any size or power limitations? A $10,000 solution is useless if the budget is $1,000. A machine the size of a car won't work if it needs to fit on a countertop. By spending just 2 minutes in this clarification phase, you have completely transformed the conversation. You've taken a vague, fuzzy problem and turned it into a well-defined set of engineering requirements. You've demonstrated a level of maturity and foresight that immediately puts you in the top tier of candidates. Now, and only now, do you move to step 2, deconstruct. You take the big, intimidating problem, build an M&M sorter, and you break it down into smaller, manageable subproblems. You'd say, okay, based on those requirements, I see this machine having 4 main functional blocks. First, we need a way to feed the M&Ms into the system one at a time. Let's call this the singulation stage. Second, we need to identify the color of each individual M&M. That's the inspection stage. Third, we need to physically direct the identified M&M into the correct bin. That's the actuation or sorting stage. And finally, we need a central controller, a brain, to coordinate all these actions. That's the control stage. This is magic. You've taken a messy concept and turned it into a clean, logical system architecture. It's organized. It's methodical. Proves you can structure your thoughts under pressure. Each of these mini problems is now far easier to solve than the original big one. Which brings us to step 3, solutionize. This is the part where you finally get to talk about technology. But you don't just pick one solution. You brainstorm multiple options for each block you define, and you discuss the trade-offs. This is critical. It shows you understand that in engineering, there's rarely a single right answer. There are just different solutions with different pros and cons. So you'd walk them through it. For the singulation stage, we could use a simple vibrating bowl feeder, which is common in industrial settings. It would shake the M&Ms and channel them down a track into a single file line. It's reliable but can be expensive and noisy. Alternatively, for a smaller scale, we could use a simple hopper that drops them onto a narrow conveyor belt. It's cheaper, but we might have to deal with occasional jams or 2 M&Ms coming out at once. Then you move to the inspection stage. For inspection, the most straightforward option is a color sensor. We'd position it right over the track where the M&M passes. It's fast and relatively cheap. However, its performance might be affected by ambient lighting. A more robust, but also more complex and expensive solution would be to use a small camera and some basic computer vision. This would let us not only identify the color, but also potentially inspect for defects like cracks or chips, which we discussed in the clarification stage. Next, actuation. Once we know the color, we need to sort it. A simple way would be to have a series of small gates or diverters along the path. The controller would open the correct gate for the red M&M, the blue one, and so on. Another faster method would be to have the M&M drop off the end of the conveyor and use a quick puff of compressed air from a targeted nozzle to blow it into the correct bin. This air jet method is very fast and has no moving parts to wear out, but it requires a compressed air source. Finally, you tie it all together with the control stage. For the controller, given the simplicity of the logic read sensor fire actuator, we could use a programmable logic controller, or a PLC, which is the standard in industrial automation. It's incredibly robust and reliable. For a smaller budget-conscious prototype, a microcontroller like an Arduino or a Raspberry Pi would be more than capable of handling the sequencing. By presenting options and discussing trade-offs for each block, you're not just building a hypothetical machine, you're conducting a design review live in the interview. You're demonstrating a depth of knowledge that goes far beyond just knowing what a sensor is. And that leads to the final expert-level step, validate. This is where you put on your what could go wrong hat. You anticipate problems and think about how to test and verify your design. You'd wrap up by saying, before building the final version, I'd want to validate a few key assumptions. For instance, I'd test the chosen color sensor with M&Ms under various lighting conditions to ensure its reliability. I'd also want to think about failure modes. What happens if an M&M gets stuck? We should probably include a sensor to detect jams. What about maintenance? We should design the machine for easy cleaning since we're dealing with a food product. And finally, we'd need a calibration routine to make sure the timing between the sensor reading the color and the air jet firing is perfectly synchronized. And that's it. You stop. You've taken them on a complete professional engineering design journey in under 10 minutes. From vague idea to a well-defined, architected, and considered solution. You didn't just answer the question, you dominated it. You proved you have a repeatable process for solving any complex problem they could ever throw at you. This clarify, deconstruct, solutionize, validate framework is your key. Practice it. Internalize it. Use it on any problem you can think of, how to automate making a sandwich, how to design a better traffic light system, anything. Because having the right mental model is half the battle. But it's still only half. Having the framework is one thing, but interviewers also want to see that you can actually build something. They want to see proof that you can take these ideas from the whiteboard to the real world. Having a mental process is great, but it's a portfolio of hands-on projects that will truly make you an undeniable candidate. And building that portfolio is a lot easier and cheaper than you think. You just need to know what to buy and where to start. And that's exactly what we're going to lay out next. The ultimate shopping list for your home automation lab that will give you 90% of the skills you need for less than the price of a new video game console. Alright, let's build your lab. This isn't just a shopping list. This is your starter pack for a new career. This is the key that unlocks the door. And the best part? We're doing this on a budget that makes sense. We're focusing on maximum impact for minimum cost. First things first, you need the brain, the central command. In the world of automation, this is the PLC, the programmable logic controller. Now you could go on eBay and get lost in a sea of used decade-old Allen Bradley or Siemens units with no software and no support. That's a recipe for frustration. We're not going to do that. We are going to buy a brand new, fully supported PLC with free software. I want you to go to the Automation Direct website and look for the Click PLC series. Why this specific one? Because it's the perfect storm for a learner. It's incredibly affordable. We're talking starting around $100 for the CPU. The programming software, Click PLC programming, is 100% free. No licenses, no subscriptions, no 30-day trials. You download it, and it's yours forever. And most importantly, the skills you learn on this PLC are directly transferable. The concepts, the instruction sets, the way you think about logic, it's the same foundation you'll use on a $50,000 Rockwell ControlLogix platform. This isn't a toy. It's a simplified, accessible version of the real deal. It's like learning to drive in a Honda Civic. It's reliable, it's forgiving, and once you master it, you can hop into a Ferrari and you'll still know where the gas pedal is. Get the most basic Ethernet-capable CPU they offer. That's your brain. Okay, a brain in a box is useless. It needs to perceive the world. It needs senses. In automation, we call these inputs. We're going to start with the most fundamental sense of all, touch. We need push buttons. Go find some standard panel mount industrial push buttons. You'll want at least two. One normally open green button for start, and one normally closed red mushroom head button for stop. These aren't the flimsy little buttons you find on a breadboard. These are heavy-duty, satisfyingly clickable components that you will physically wire to your PLC. This simple act of wiring a button to an input terminal is a core skill. You'll learn about sourcing versus syncing, NPN versus PNP, and the critical difference between normally open and normally closed contacts. Getting these buttons, which cost just a few dollars each, will teach you more than 100 hours of theory. Now let's give our system a rudimentary form of sight. We need a sensor. We're not going to break the bank on a complex vision system. We're going to get a simple inductive proximity sensor. This is a little metal cylinder that can detect when a metallic object is near it, without ever touching it. It's magic. It's the sensor that tells a machine a part is in place, a door is closed, or a piston is retracted. They are the invisible eyes on every factory floor. Again, you can get a perfectly good one for $20 to $30. Wiring this sensor will teach you how 3-wire DC sensors work, which is a massive category of devices you'll encounter every single day in the field. So now our brain has a sense of touch and a sense of sight, can perceive the world. But what can it do? It needs to act. It needs to communicate. It needs outputs. The simplest form of action is to give a signal. We're going to get a small stack light, or at the very least a couple of 22mm panel mount indicator lights, one green, one red. When you press the green start button, you're going to program the PLC to turn on the green light. When you press the red stop button, it will turn on the red light. This sounds incredibly basic, but this is the hello world of automation. This is the moment the digital world of your code reaches out and affects the physical world. It's a profound moment. You're making something happen. You are controlling a machine. This simple setup teaches you how to wire output cards, how to handle different voltages, and the fundamentals of state-based logic. So far, we have a brain, senses, and a voice. We have a complete, albeit simple, automated system. Total cost so far? Probably under $200. But we can do better. We can give it a face. We need to add an HMI, a human-machine interface. This is the touchscreen display that allows an operator to interact with the machine. This is where you'll build the graphics, the buttons, the data displays that make a complex system understandable to a normal person. Just like with the PLC, we're going to stick with the Automation Direct ecosystem for simplicity and cost. Look for their Seymour Micro line. These are small, incredibly affordable touch panels, often available for less than $200. And just like the PLC, the software is 100% free. Getting one of these and connecting it to your Click PLC over Ethernet is a game changer. Now you can create a start button on the screen that does the same thing as your physical green button. You can display the status of your proximity sensor. You can make the on-screen background flash red when the system is stopped. Learning to program in HMI is a distinct and highly valuable skill. You're not just a programmer anymore. You're a designer. You're thinking about user experience, about clarity, about making the machine easy and safe to operate. Finally, how do all these pieces talk to each other? The brain, the face, they need a nervous system. And that nervous system is Ethernet. You don't need anything fancy here. A simple, unmanaged Ethernet switch, the same kind you might use for your home network, will do the trick. You can get one for $20. You'll also need a few Ethernet patch cables. This is how your PLC, your HMI, and your programming laptop will all communicate. By connecting these devices, you will learn about IP addresses, subnets, and the basics of industrial networking. You'll learn how to establish communication between a controller and an HMI, a task you will perform thousands of times in your career. So let's recap your shopping list. One Click PLC with an Ethernet port, a small 24-volt DC power supply to run everything, a couple of push buttons, an inductive proximity sensor, a couple of indicator lights, one Seymour micro HMI, and a cheap Ethernet switch. That's it. That is your home lab. What's the total damage? If you're smart about it, you can get every single thing on this list brand new for under $500. That's less than a new PlayStation 5. But unlike a video game console, this purchase is an investment that can realistically lead to a six-figure income. Every single component is a building block for a specific marketable skill. With these parts sitting on your desk, you have a miniature, fully functional automation cell. You have the hardware to learn PLC programming with ladder logic. You have the hardware to learn HMI design and screen development. You have the hardware to learn physical wiring of real-world inputs and outputs. You'll learn about control voltages, circuit protection, and grounding. You'll learn how to troubleshoot not just code, but physical devices. You will have a complete, end-to-end system that you built yourself. The confidence that comes from taking this box of parts and breathing life into it is immeasurable. It's the difference between reading about how to swim and actually jumping in the water. Now you have the gear. You've assembled your toolkit. You're standing at the edge of the pool. But before you can jump in, you need a plan. You need the instructions. You need the software that will be the ghost in this machine. And the very first step is writing the single line of code that started it all for so many of us. The line of code that takes a signal from the real world, and in response makes a light turn on. And in the next part, we're going to download all the free software, get it installed, and write that first magical line of logic together. Alright, let's do this. Let's build our digital workshop. This is the moment where the abstract ideas of automation become tangible software sitting right on your own computer. This is where you get the tools. And I want to be crystal clear. Every single piece of software we are about to download is 100% free. You will not spend a dime to get a professional-grade automation development environment running on your laptop. This isn't some cheap knockoff simulator. This is the real deal, provided by the biggest players in the industry for the exact purpose of learning. So what are we actually grabbing? Think of it like building a robot. We need three key things. First, we need the robot's brain. This is the programmable logic controller, or PLC. Second, we need a way to talk to the brain, to teach it, to give it instructions. That's the programming software. And third, we need a way for the robot to communicate with us in the outside world, a screen, a face. This is the human-machine interface, or HMI. The brain, the language, and the face. Now, in the United States, one ecosystem dominates the industrial landscape, especially in manufacturing. That's Rockwell Automation and their Allen Bradley brand. If you walk into a major factory in North America, the odds are overwhelmingly high that you will see their gear. So that's what we're going to learn. Learning this specific platform makes your resume instantly recognizable and valuable to thousands of US companies. We're not just learning to code. We're learning the specific dialect that American industry speaks. The software names might sound a little intimidating at first, but don't worry. The main programming environment is called Studio 5000 Logix Designer. The HMI software is called FactoryTalk View Studio. And the special software that lets them all talk to each other is called RS Links. Normally, a single license for Studio 5000 can cost more than a used car. But we're going to get the free learner's version. So grab a coffee, open up your web browser, and let's get started. The very first thing we need to do is go to the Rockwell Automation website. Just search for Rockwell Automation Software Download. You'll find their Product Compatibility and Download Center, or PCDC. This is our treasure chest. You will have to create a free account. Don't skip this. Just use your email, create a password. It's a necessary step to access their entire library of free tools. Go ahead and do that now, I'll be here. Okay, account created? Logged in? Perfect. In the search bar, the first thing we're going to type is RS Links Classic Lite. Think of RS Links as the universal translator, the nervous system of our whole setup. It's a small but absolutely critical piece of software that allows our programming software to find and communicate with our virtual PLC. Without it, it's like trying to talk to the brain without a mouth. You'll see a download link. We want the latest version. It's a free version called Lite, which is all we need. Go ahead and click download. It'll ask you to agree to some terms and conditions. Just accept and start the download. That's piece number 1. Next up, we need the brain itself. Since we don't have a physical $1,000 PLC sitting on our desk, we're going to use an emulator. An emulator is a piece of software that pretends to be a physical piece of hardware. It creates a virtual PLC that lives entirely inside your computer. It is, for our purposes, identical to the real thing. This is one of the most powerful learning tools you will ever use. Back in that same download search bar, you're going to type Studio 5000 Logix Emulate. See that? It's the brain in a box. We're going to download this as well. Again, pick the latest version available. The download will be a bit bigger, so let it run in the background. While that's downloading, let's go get the main event. The programming software itself. This is the one that lets us write the logic. It's the software you'll be staring at for much of your career. In the search bar, type Studio 5000 Logix Designer. Now this is important. You will see many versions. The full versions are locked and require a paid license. But hidden in the list, you will often find a version specifically for the emulator, or sometimes it's bundled with the Lite edition. What you're looking for is the free, unlicensed version that will allow you to program the Logix Emulate controller we are currently downloading. Sometimes this is labeled as a trial, but it's a version that will work with the emulator indefinitely. Make sure the version of Logix Designer you download matches the version of Logix Emulate you downloaded. If you got version 33 of Emulate, get version 33 of Designer. This compatibility is key. Go ahead and get that download started. So now you should have 3 files downloading: RS Links Classic Lite, Studio 5000 Logix Emulate, and Studio 5000 Logix Designer. This is your core toolkit. This is your digital workshop. Once everything is downloaded, we have to install it. And the installation process for industrial software is a little different than installing a video game. It's a bit more particular. So follow these tips to save yourself a massive headache. First, and this is non-negotiable, install them in the correct order. You must install RS Links Classic Lite first. Always. This sets up the communication foundation that everything else is built on. If you install the other software first, it will get confused because it can't find the nervous system it needs to function. So RS Links first. Then you can install Logix Emulate and finally Logix Designer. Second tip. When you go to run the installer file, don't just double-click it. Right-click on the file and select Run as Administrator. This is incredibly important. This software needs to install deep-level system services and drivers, and if you don't give it administrator privileges, the installation will likely fail in a very confusing way halfway through. Save yourself the trouble. Always run as administrator. Third tip, be patient. This is a massive professional software suite. The installation can take a while. It might look like it's stuck. It might ask you to reboot your computer multiple times. This is normal. Just follow the on-screen prompts, let it do its thing and don't panic. Go refill that coffee. A standard installation for all 3 components might take anywhere from 30 minutes to over an hour, depending on your computer's speed. And speaking of your computer, you don't need a top-of-the-line gaming rig for this. A modern laptop with a decent processor, an i5 or a Ryzen 5, and at least 8 GB of RAM will work just fine. 16 GB is better, but 8 will get the job done for learning. You also need to be running a professional version of Windows. Unfortunately, this software doesn't run on Mac OS or Linux. So to recap the action plan: 1. Download RS Links Classic Lite, Studio 5000 Logix Emulate, and Studio 5000 Logix Designer from the Rockwell website. 2. Install them in order. RS Links first, then Emulate, then Designer. 3. Remember to right-click and run as administrator for every single installation. Go ahead and get that done. Get everything installed. When you're finished, you'll have a new set of icons on your desktop. You'll have the keys to the kingdom. Your computer is no longer just a tool for browsing the internet. It is now a fully functional automation development studio. The same exact tools that are used to program assembly lines for electric cars, bottling plants for your favorite soda, and automated systems at theme parks are now sitting on your hard drive, waiting for you. Take a moment to appreciate what you've just done. You've built the workshop. You've gathered the tools. The foundation is laid. All that's left is to open the door, turn on the lights, and make something happen. And that is precisely what we're going to do in the very next part. We will launch the software, configure our virtual brain, establish communications, and together we will finally write that first beautiful magical line of ladder logic. Alright, the moment of truth has arrived. Fire up your virtual machine, and let's find the icon for Studio 5000 Logix Designer. For me, it's right here on the desktop. Give that a double click. This is it. This is the digital workshop where billions of dollars of industrial processes are born and brought to life. Every time you open this software, remember, you are stepping into the role of a creator. Now a little splash screen will pop up, and then you're presented with the main window. It might look a little intimidating at first. Lots of gray space, menus, buttons. Don't worry. We're going to make sense of it all one piece at a time. The very first thing we need to do is create a new project. Think of this as laying the foundation for a new house. Go to File in the top left corner and click New Project. This dialog box is critical. It's asking us, what kind of brain are we going to be talking to? In the physical world, you'd have a specific model of controller, a compact Logix or a control Logix, and you'd have to pick the exact one from this list. But we are in the beautiful world of emulation. We are using a virtual brain. So on the left under Type, we need to find the Logix Emulate controller. It's the one with the little computer monitor icon. Click on that. Now on the right, it's asking for a name. This is more important than you think. Naming conventions are a huge deal in the real world. You can't just call a project as fast when it's controlling a critical chemical reactor. For today, let's be descriptive. Let's call it project. Using underscores instead of spaces is a common and very good practice. Click Next. Okay, this next screen is setting up the specifics of our virtual brain. The revision is like the firmware version of the controller. We'll just leave it at the default that Studio 5000 selected for us. Now the chassis type. A chassis is the physical rack, the body that the controller, the brain, plugs into. Our emulator mimics a real chassis, so we'll leave that as is. But here's the important part, the slot. We have to tell the project which slot in this virtual body our brain is going to live in. Remember when we set up the emulator in the last part? We put our virtual CPU in slot 2. If we get this wrong, our project will be trying to talk to an empty slot, an empty room. It will never find the brain. So make sure you change this number to 2. This is a classic rookie mistake and you just learned how to avoid it. Go ahead and click Finish. The software will now start building the project file. It's creating the entire digital architecture, the file structure, the memory map, everything we need. And there we are. Welcome to the controller organizer. This tree view on the left is the entire anatomy of our automation program. It looks like a lot, but we're going to focus on just one tiny part of it today. But before we can write a single command, we have a problem. We have our digital workshop here in Studio 5000, and we have our virtual brain running over in the emulator. They're two separate entities. They live in the same house, our computer, but they aren't talking to each other. They don't know the other exists. We need to build the nervous system. We need to create the communication pathway that allows our commands to travel from the workshop to the brain. In the Rockwell automation world, that nervous system is a piece of software called RS Links. Let's go find it. Go to your Start menu, look for the Rockwell software folder, and open RS Links Classic. This program's entire job is to manage communications. It's the universal translator, the switchboard operator for all of your automation equipment. Once it's open, go to the Communications menu at the top and select Configure Drivers. A driver is just a specific protocol, a specific language that we'll use to talk. Since our virtual controller lives on a virtual network backplane, we need to add the virtual backplane driver. From the Available Driver Types dropdown, find Virtual Backplane, SoftLogix 58XX, Emulate 55XX, and click Add New. You can just leave the default name and click OK. And that's it. You can now close this window. Now look at the main RS Links window. You should see our new driver running. If you click the little plus sign next to it, it expands and RS Links will start browsing that virtual network. And bingo! There it is. O2 Logix 5550 Emulate. That's it. That's our brain. RS Links can see it. It has established a connection. That is a massive step. We have officially built the nervous system. Our two separate programs are now aware of each other. Let's go back to Studio 5000. It's time to connect our workshop to that nervous system. At the top, go to Communications and select Who Active. This opens up a window that looks almost identical to RS Links. It's basically peering through RS Links to see what's out there. You should see the same virtual backplane driver we just created. Expand it. And there, once again, is our controller in slot 2. Click on it. Select it. This is the moment you tell your project, hey, that brain over there in slot 2? That's the one I want to talk to. That's my target. In the bottom right, you'll see a button that says Go Online. Don't click it yet. First, we need to download our empty program to it. A download sends the blueprint from our workshop to the brain, overwriting whatever was there before. Click the download button. It'll pop up with a confirmation. It's a scary-looking warning, but since our controller is blank, we have nothing to worry about. Click download again. You'll see a progress bar. It's transferring the data, compiling, and now it's asking if we want to change the controller back to remote run mode. Yes, we do. Click yes. Look at the top bar. The remote run indicator is solid green. The I/O is flashing green. And most importantly, it says connected to project. We are in. We are live. We are connected directly to the processor's mind. We are looking at the code that is actively being scanned, being executed thousands of times per second. Right now it's executing nothing. An empty set of instructions. Let's change that. On the left, in our controller organizer, expand the main program. Then, expand the main routine. Double-click on main routine to open it up. This is it. The blank canvas. That line with the number 0 and the word END on the right. That is a rung of ladder logic. It's the end of the ladder. We need to add a rung above it. Look at the toolbar at the top. You'll see a bunch of icons that look like electrical symbols. Find the one that looks like a ladder with a little green arrow. It says Add New Rung. Click it. Boom. A new empty rung appears. A blank slate for our first command. Now, we will write the most fundamental, the most basic, the most important pattern in all of automation, the if-then statement. If this input is on, then turn that output on. The light switch and the light bulb. Find the icon that looks like two parallel lines like a normally open contact on a schematic. It's called an XIC, or examine if closed. Click on it and then click on the new rung you just created. It will drop right in. Now find the icon that looks like a circle, an OT, or output energize. Click that and drop it on the right side of the rung. You have just created the structure for a logical command. But it's not complete. The program is asking, examine what? Energize what? It needs names. It needs variables, or in PLC terms, it needs tags. Double-click on the question mark above the XIC contact. A text box will appear. Type in the word switch. Hit enter. A little box pops up. The program is saying, I've never heard of switch before. Do you want to create it? Yes, we do. Click New. In the window that appears, just click Create. We just created our first tag, our first piece of memory in the controller. Now do the same for the output. Double-click the question mark over the OTE coil. Type underlight. Hit enter. The box pops up again. Click New, then click Create. Look at what you've done. You have written a complete logical sentence. If my_switch is on, then turn my_light on. It's beautiful. It's perfect. But this code only exists on our computer, in our workshop. The brain in the emulator is still running the old, blank program. We need to send this single line of genius over to the controller. Because we are online, we can't just do a full download. We have to assemble this one rung and insert it into the running code. At the top of the screen, there's a button with a computer chip and a green check mark. Hover over it. It says Finalize All Edits. Click that button. A confirmation box appears. Are you sure you want to finalize? Yes. 1,000 times yes. Click Yes. The bars will turn green. It's done. You did it. That single line of code, your first line of ladder logic, is now inside the processor. It is being scanned and executed right now thousands of times per second. It is official PLC code. Now for the magic. How do we test it? How do we flip the switch? Right-click on the tag my_switch. In the menu that appears, go down to toggle bit. A bit is a 1 or a 0, on or off. By toggling it, you are manually reaching into the brain's memory and flipping that switch from off to on. Click it, and just like that, look, the XIC instruction for switch is highlighted green. The power is flowing across the rung. And the OT coil for light is now also highlighted green. You turned it on. You wrote a command, sent it to a processor, and manipulated its memory to execute your logic. You just became a programmer. Think about that for a second. With a few clicks and a bit of logic, you reached into a virtual machine and forced it to do your bidding. That feeling, that spark of creation and control, that's the core of automation. It's the same fundamental principle that runs a single conveyor belt or an entire oil refinery. You've tasted it. Now let's build on it. Because turning on a light is cool, but it's the hello world of our industry. Proves the concept. But the real power, the reason this career is so lucrative and essential, is what you do next. Let's make that light do something a little more intelligent. Go back to your ladder logic. Let's say this light isn't just a light. Let's pretend it's the motor for a pump. You don't want the pump to just turn on and stay on forever. You want it to run for exactly 10 seconds to fill a small tank, and then turn off automatically. How would you do that? You can't just sit there with a stopwatch and toggle the bit off manually. That's not automation. This is where you graduate from simple on-off commands to using instructions. Inside your programming software, you'll find a whole toolbox of logical blocks. One of the most common is the timer. Think of it like a programmable stopwatch that lives inside the PLC. So let's modify our logic. We'll keep our start_button instruction, but when you press it, instead of turning on the light directly, it will start a timer. We'll drag a timer block onto our rung and give it a name like pump_timer. We'll configure its preset for 10,000 milliseconds, which is 10 seconds. Now the PLC is keeping track of time. But how does that help us? Well, the timer itself has its own internal bits. The most important one for us is the done bit. This bit will automatically turn on the very instant the timer reaches its 10-second preset. So we create a new rung of logic. On this rung, we'll put an instruction that looks at the pump_timer's done bit. But we want the pump to be on while the timer is running, not after it's done. So we'll use another one of the timer's bits, the timer timing bit, or TT bit. This bit is true only when the timer is actively counting. Our new logic will look like this. A rung with an instruction that looks at the TT bit of pump_timer, and if it's true, it turns on our output, light, which we're pretending is our pump. Now download and run it. Toggle the start_button bit on. You'll see the timer start counting up 1, 2, 3, and all the while the light output is on. The pump is running. As the timer hits 10 seconds BAM, the TT bit turns off, and your light goes dark. The pump stops. Automatically. You just created a time sequence. This isn't just turning something on anymore. This is defining a process. This is the logic that fills every bottle of soda, that cures paint on a car for the perfect amount of time, that mixes ingredients in a batch of cookie dough with perfect precision. It's all just timers, counters, and basic logic scaled up. This brings us to the fourth major step in your journey. You've learned the fundamentals of what automation is. You've chosen your software and hardware path. You've written your first lines of code and created a simple, timed process. Step 4 is learning how humans actually interact with all this code. Because the operator on the factory floor, the person making sure the machine runs smoothly all day, they will never see your ladder logic. They will never open up Studio 5000 or TI Portal. Giving them access to the raw code would be inefficient, confusing, and incredibly dangerous. Instead, they interact with the machine through a human-machine interface, or HMI. It's usually a touchscreen monitor mounted on the machine, or on a control panel nearby. It has buttons, status indicators, graphs, and readouts. It's the face of the machine. Your PLC program is the brain, but the HMI is the face. It's how the brain communicates with the outside world and how the world gives commands back to the brain. As an automation engineer, you're responsible for programming both. The HMI software is often made by the same company as the PLC. For Allen Bradley, you'll use software like FactoryTalk View Studio. For Siemens, you'll use WinCC. The concept is the same across all of them. You design screens by dragging and dropping objects, buttons, numeric displays, alarms, and then you link those objects to the tags in your PLC program. Let's go back to our simple pump example. On your HMI development software, you'd create a new screen. You drag a button object onto it and label it Start Pump. You drag another one and label it Stop Pump. Then you drag a little indicator light, maybe a circle that can change color, and place it next to the text Pump Status. Now comes the magic. You click on the Start Pump button you just created. You go into its properties. There will be a field for connection or tag. In that field, you will link it directly to the Start_button tag in your PLC program. You do the same for the Stop Pump button, linking it to a new Stop_button tag you'd create in your logic. For the indicator light, you'd link its visibility or color property to the light output tag in the PLC. You'd set it up so if the my_light tag is a 0, the circle is red, and if it's a 1, the circle is green. Now imagine the whole system running. The operator walks up to the screen. They see a simple, intuitive interface. They press the Start Pump button on the glass screen. Because you link that button to the Start_button tag, the HMI sends a command over the network to the PLC, telling it to turn that bit to a 1. Your PLC, which is constantly scanning your logic, sees that the Start_button bit is now true. It starts the timer. The timer's TT bit becomes true, which in turn activates the light output. The real-world pump turns on. Simultaneously, because the my_light output bit is now a 1, the PLC sends that status information back to the HMI. The HMI sees that the tag it's monitoring is now true, and it follows the rule you gave it. It changes the color of the pump status indicator on the screen from red to green. The operator gets immediate visual feedback that the pump is running. 10 seconds later, your PLC timer finishes. The TT bit goes false, the light output turns off, and the physical pump stops. The PLC reports this change back to the HMI, which updates the on-screen indicator back to red. This is the handshake. This is the complete system. The HMI provides the simple, safe, graphical controls for the operator. The PLC executes the complex, high-speed, and reliable logic that actually runs the machine. And you, the automation engineer, are the architect of both. You build the brain and you design the face. You create the entire conversation between human and machine. Learning to create clean, intuitive, and helpful HMI screens is a skill all on its own. It's part graphic design, part user experience design, and part programming. And it's absolutely essential. You could write the most brilliant, efficient PLC code in the world, but if the operator can't figure out how to start the machine, reset a fault, or understand what an alarm means, your program is a failure. So your next step is to open up that HMI software that came with your suite. If you downloaded Studio 5000, you have access to Factory Talk View. If you have TIA Portal, you have WinCC. Start a new project. Connect it to the virtual PLC you're already running. Try to recreate that simple pump control screen. Make a start button, a stop button, and an indicator. Link them to the tags you already made. Experience that moment when you press a button you drew on a screen and see the logic you wrote in a separate program react in real time. When you make that connection, you fundamentally grasp the architecture of 90% of the automated systems in the world. You understand the relationship between the operator, the interface, and the controller. You now possess the core foundational knowledge of an automation and controls engineer. You know what the hardware is, you know what the software is, you know how to write basic logic, and you know how that logic is controlled by a human operator. This is a massive milestone. But having the knowledge is one thing. Turning that knowledge into a six-figure career is another thing entirely. You have the tools. You've built a small campfire. Now you need the map that shows you how to get out of the woods and into the city. The fifth and final step is the bridge from learning to earning. It's about how you take these skills, package them, and present them in a way that makes a company want to pay you for them. It's about building proof, making connections, and acing the interview. This last step is what separates the people who tinker with PLCs as a hobby from the people who build incredible careers with them. And it's the most important step of all. And that final step, the one that ties everything together, is this: forge your professional identity and commit to lifelong learning. This isn't just about applying for jobs. This is about transforming yourself from someone who knows about automation into an automation professional that companies are desperate to hire. It's the final polish, the strategic presentation of all the hard work you've done in the first 4 steps. Let's break this down into 2 critical parts. First, forging your identity. This starts with your resume. I want you to burn your old resume. Seriously, The one that lists your coursework and your summer job at a coffee shop? It's gone. Your new resume is not a history of employment. It is a marketing document for a product, and that product is you, the automation problem solver. Every single point on your resume, especially for your projects, must be framed using the STAR method: situation, task, action, and result. This is non-negotiable. A beginner writes, programmed a PLC for a home project. A professional writes, designed and implemented a PLC-based control system for a simulated bottle capping line in a home lab environment. That's the situation and task. I utilized ladder logic on an Allen Bradley Micro 820 to sequence 3 pneumatic solenoids and a DC motor, integrating feedback from 2 inductive proximity sensors. That's the action. This resulted in a system capable of achieving a 99.5% successful capping rate at a simulated speed of 40 bottles per minute, demonstrating a comprehensive understanding of discrete I/O and sequential logic. That's the result. Do you see the difference? One is a statement, the other is a story of competence. It screams, I don't just know the theory, I have solved a problem and I can prove it with data. Every project from your home lab, every relevant academic project, needs to be rewritten in this format. Quantify everything you can. Use numbers. Percentages, speeds, efficiencies, error reduction. Numbers are the language of engineering and business. They cut through the noise and prove your value. Next, your LinkedIn profile. This is not just an online copy of your resume. It is your digital headquarters. Get a professional headshot. No selfies from your car, no pictures from a party with your friends cropped out. A simple, well-lit photo against a neutral background. Your headline should not just be student at X university. It should be aspiring automation and controls engineer PLC, and HMI programming robotics industrial networking. Immediately, a recruiter knows exactly who you are and what you want. Your About section is the most underutilized real estate on the internet. Don't just list your skills. Tell your story. My fascination with how things work began when I took apart my first remote control car. That curiosity has evolved into a passion for industrial automation. Over the past year, I've dedicated myself to learning the fundamentals, building a home lab where I designed and programmed a Mention Your Best project. And I am now seeking an opportunity to apply my skills in PLC programming and systems integration to solve real-world manufacturing challenges. This narrative is powerful. It shows passion, initiative, and direction. After you've built this foundation, you use LinkedIn as a tool. Connect with recruiters at companies you admire. Connect with controls engineers who work there. Don't just send a blank request. Add a note. Hi name. I'm a student passionate about automation and I was really impressed by the robotic welding cell your company showcased on YouTube. I'd love to connect and follow your work. Engage with their content. If an engineer from a target company posts about a new VFD they're using, leave a thoughtful comment. Not just cool, but that's a powerful drive. I've been experimenting with the PowerFlex 525 in my lab, and am curious how the setup for safe torque off on this model compares. You are now on their radar. You are no longer a random applicant. You are a peer in training. Finally, your project portfolio. This could be a simple, clean website or even a well-organized GitHub repository. For every project, you need more than just a picture. You need a detailed write-up. What was the goal? What hardware and software did you use? What were the challenges you faced and how did you overcome them? Include your code, but make sure it's clean and well commented. Include a wiring diagram. Even better, embed a short 60-second video of the project in action. A recruiter can watch that video and in 1 minute, understand your capabilities better than from reading a 2-page resume. This is your proof. It's undeniable. Now for the second half of this final step. Committing to lifelong learning. Getting your first job is not the finish line. It is the starting line of a marathon. The field of automation is changing at a blinding pace. The technologies you master today might be legacy systems in 10 years. The people who build incredible, resilient careers are the ones who embrace this change and never, ever stop learning. I want you to adopt the mindset of a T-shaped engineer. The vertical bar of the T is your deep core expertise. Right now, that might be Allen Bradley PLC programming. You need to know it inside and out. But the horizontal bar of the T is your broad knowledge across related domains. You need to understand the basics of industrial networking. What's the difference between Ethernet/IP and Profinet? You need to understand robotics. How do you establish a handshake between a FANUC robot and a Siemens PLC? You need to understand cybersecurity. Why is it a terrible idea to connect a plant floor network directly to the internet? You need to be aware of data analytics and machine learning. How can we use the data from our sensors to predict when a motor will fail? You don't need to be a world expert in all these things, but you need to speak the language. This breadth makes you infinitely more valuable. It allows you to see the bigger picture, to work effectively with other teams, and to design more robust, integrated systems. So how do you do this? First, become a voracious consumer of information. Follow industry publications like Automation World and Control Engineering. Subscribe to the YouTube channels of major suppliers like Siemens, Rockwell, Fanuc, and Cognex. They are constantly releasing new product information and case studies. Second, join a professional organization. The International Society of Automation, or ISA, is a fantastic place to start. They offer certifications, training, and networking events. Being in a room with experienced engineers is an education in itself. Listen to the problems they're talking about. Those are the problems you'll be paid to solve in the future. Third, always be working towards your next certification. Once you're in a role, your company will often pay for this. Maybe it's a formal certification from a vendor like Siemens or Rockwell. Maybe it's a networking certification like the CompTIA Network Plus or even a CCNA. These formal credentials validate your skills and open doors to higher-level roles. The mindset shift is this: your education did not end when you got your diploma. It began. You have to dedicate time every single week to learning something new. Maybe it's reading a technical manual for a new sensor. Maybe it's watching a tutorial on structured text programming. Maybe it's learning the basics of Python for data scripting. This proactive curiosity is what separates the technicians from the engineers, and the engineers from the architects of future systems. So let's bring it all together. The 5 steps on this journey. Step 1. You built a rock-solid foundation, mastering the non-negotiable fundamentals of electricity, logic, and control. Step 2. You brought that theory to life, building your own home lab to gain priceless hands-on experience. Step 3. You chose your path, specializing in a specific platform and technology stack to become a true expert, not a jack of all trades. Step 4. You stepped out of the lab and into the community, networking strategically and building a body of proof that showcases your skills. And Step 5. You polished it all, forging a professional identity that markets your value and committing to the lifelong learning that will sustain your entire career. This is the roadmap. This is the path from zero to a 6-figure career, solving some of the most interesting and important challenges on the planet. You will be the person who makes factories more efficient, who makes products safer, who enables manufacturing feats that were impossible just a few years ago. The gap between where you are right now watching this video and walking onto a plant floor to commission a system you designed is not a chasm of luck or genius. It is a series of deliberate, achievable steps. You now have the map. You have the complete strategy. The only thing left to do is to take the first one. If this roadmap has given you clarity and a sense of direction, do me a favor and hit that like button. It tells the algorithm that this is valuable information and helps other people just like you find it. Subscribe and turn on notifications so you don't miss the next deep dive into the tools and tactics of modern engineering. And most importantly, I want to hear from you. Go down to the comments right now and tell me which step you are starting with today. Are you ordering your first PLC? Are you revamping your LinkedIn? Are you starting your first project? I read every single comment, and I want to see you start this journey. Thank you for your time. Now go build something incredible.